Hi, I'm going to talk about computing approximate center points in polynomial time. And I'm going to start by defining what a center point actually is. A center point is essentially going to be a generalization of the one-dimensional notion of a median to higher dimensions. And in one dimension, the definition of a median is quite simple. It's simply going to be the point with 50% of the points on either side of it. Now, you can ask how such a definition is going to extend to higher dimensions. And now an immediate problem presents itself. There is no notion of sides in higher dimensions. So for instance, let's say you have a point set that's specified by the set of blue points. And for one direction V1, and you draw the hyperplane or orthogonal to V1, you have some set of points on either side of this hyperplane. But for a different direction V2, you could have a different number of points on either side. So how do you decide like a canonical version of side to compute such a notion of a median? And this naturally motivates the definition of a depth function. And this is going to be defined for a point set capital X, some candidate point little x, and some direction V. And it's going to be computed as follows. You essentially project all your points, capital X and little x, onto the direction V. And you count the number of points whose projections are less than x, and the number of points whose projections are greater than x. And you take the minimum of these two. So for some point set x here, capital X here, in higher dimensions, and let's say that the point that you want to test for its depth is this red point here. And V specifies this hyperplane passing through the red point little x. And you count the number of points on one side of this hyperplane, and you count the number of points on the other side of this hyperplane, and you take the minimum of these two to compute the depth. And now you can ask this natural question. Can I get a point in higher dimensions which has depth half in every single direction? Note that this generalizes the one-dimensional notion of the median that we saw before. And unfortunately, you can show that this is not always possible. So this is a consequence of a classical result in convex geometry by Helly from 1923. And he showed that there are point sets for which the worst case depth is at most 1 over d. Okay, so you can't beat this 1 over d factor for certain point sets. And now the definition of a center point is any point whose depth in any direction is at least 1 over d. Okay, and observe that in the specific setting, when d is equal to 1 in 1D, the center point coincides with the definition of the median. Okay, now we're going to move on to the main question that we tackle in this talk. Can we compute such center points in polynomial time? So can we compute center points in time that's polynomial in n, the number of points in the point set, and d, the dimension? Unfortunately, the best known polynomial time algorithms only give the following worst guarantee. They only give you a point with depth 1 over d squared, as opposed to the information theoretically optimal 1 over d. And this was proven in this paper by Clarkson, Epstein, Miller, Sturtevant, and Teng from 1993. And as I just stated, this result is suboptimal by a factor of d in the denominator. And the approach that we're going to take in this talk is whether we can build an approximate a point whose approximate depth is 1 over d instead. And what is this notion of approximation? I'm going to define it now. To define this notion, we're going to start by defining these directional quantiles that I'm going to denote with QV. And for any direction V, QV is going to be the 1 over d plus 1th quantile of the points when projected along V. So I'm going to project the points along V, and I'm going to look at the smallest point such that at least a 1 over d plus 1 fraction of them are less than x. And then this is simply the definition of the quantile. And now any valid point with depth omega 1 over d is such that its projection along every direction V is greater than the quantile QV. Okay? And the notion of approximation that we will use in this paper will be defined by some error parameter epsilon. And we're going to relax the set of linear constraints in the equation here by an epsilon factor. So we're only going to ask for a point which approximately satisfies all of these linear constraints. And we're going to measure our runtime additionally as a function of epsilon. And pictorially, what does this relaxation actually mean? So here I've drawn the set of linear constraints that we saw on the previous slide. For visualization purposes, I've only plotted 3 of them. And now, instead of asking for a point in this smaller red triangle, I'm going to relax each of these linear constraints by an epsilon factor. And I'm only going to ask for a point in like the larger purple region drawn here, as opposed to the smaller red region that we saw on the previous slide. And what is the main result of this paper? The main result of this paper is the existence of an approximation algorithm that runs in polynomial time, and it computes an epsilon approximate center point in time that's polynomial in n, d, and 1 over epsilon. And another way of viewing this result is to view it in the setting of smoothed analysis, where we can show that this implies that you get an omega 1 over deep depth point for a smooth point set. So if you take the point set and add a little bit of Gaussian noise to every point, then the point that this algorithm returns is an exact 1 over d depth point for the smooth point set. And in contrast to previous methods for computing these types of center points, this algorithm uses techniques from continuous optimization, and it's basically a variant of approximate gradient descent. And the key contribution is in the computation of the approximate gradients used in this algorithm. So now I'm going to talk about the algorithmic approach that we use to obtain our results. And it's going to be an iterative algorithm similar to gradient descent, and it consists of the following 2 steps. In the first step, we compute an approximate gradient. And then in the next step, we use the approximate gradient for the first step to obtain an estimate. And we're going to repeat these processes until we converge to a good estimate of a center point. And the key technical contribution is that we show how to use a technical tool called the radial isotropic transformation in computing these approximate gradients. And the number of iterations, the number of times we need to run this algorithm depends on the error parameter epsilon. Okay, so what approximation guarantees do we need on this approximate gradient? So for simplicity in the rest of this talk, I'm going to assume that we're only going to compute the gradient at 0. The generalization to an arbitrary point will be straightforward. So let's say we're going to start with our current iterate being 0. And let's say that V is a direction with low depth. Okay, so the origin is a point with low depth, and V is a direction which certifies that it has low depth. So that means that the number of points which are less than the origin when projected along V are at most n over 4d. Okay, so the depth is less than 1 over 4d along V. And the guarantee that we will require on the approximate gradient g hat is that it has positive correlation with all such directions V. So we want a g hat to satisfy this property, that is inner product with any direction which certifies low depth is bounded away from 0. And the idea is that if you take a gradient step along g hat, you're improving your depth along all these directions V along which the depth is 0. And if you set the step size correctly, you also ensure that you don't ruin the depth along directions which already have large depth. Okay, but how can you compute such an estimate g hat? And to compute such an estimate, we use a technical tool called the radial isotropic transformation. And it's going to be defined as follows. For some point set capital X, we say that R is a radial isotropic transformation if the rescaled points after passing through the linear transformation R are isotropic. Okay, so I'm going to transform each of these points with respect to R, and I'm going to rescale them. And the second moment after this rescaling, it's a constant factor times the identity. And you should think of this as really being like a robust version of the isotropic transformation, which does not depend too much on the lengths of any single one data point. And you can show that such a transformation exists almost everywhere. over the point set capital X. And when such a transformation exists, it's approximately computable in polynomial time. Okay. So now how can we use this technical tool to compute an approximate gradient? Let R be the radial isotropic transformation for our point set capital X. So it satisfies this property that the rescaled data points are isotropic. And then we're going to consider the weighted sum. So I'm going to rescale all the data points by the norm of their transformations. And that average is going to function as my approximate gradient. So why is g hat defined in this equation here an approximate gradient? And now the computation is going to go as follows. First, we make the following observations. The inner product of g hat with some direction v, recall that g hat is the approximate gradient, and v is a point with low depth. And I can multiply g hat by r and multiply v by r inverse. And I can expand this using our definition of the approximate gradient that we saw on the previous slide. Okay. And now I'm going to make a few more definitions. I'm going to rescale R inverse V, the second term in this inner product in the previous equation. And I'm going to call that V tilde. And I'm going to define these two subsets of N, these two subsets of the data points. The first is the set of points that I'm going to call the set of good points, denoted by script G here. And these points are going to be positively correlated with V. So their projections along V are greater than the projections of the origin. And I'm going to define analogously a set of bad points, which are going to be all other points in the point set. And since V is a direction of low depth, the number of points whose projection along V is less than 0 is quite small. And by our assumption, the size of the bad point set is less than n over 4d. Okay? And now I'm going to show that this correlation is positive. The correlation of g hat with v is positive. Now, why is this true? I'm going to multiply this equation by n on the left-hand side. So n times the inner product of r times the approximate gradient with v tilde. And I'm going to write it down in terms of the sum over the good and bad points separately. And then now note that the second term, each of these inner products is of value at most 1 due to the Cauchy-Schwarz inequality and the fact that each of these vectors is bounded by 1 in Euclidean norm. So by Cauchy-Schwarz, each one has magnitude at most 1. And since the size of B is at most n over 4d, the negative term is going to be greater than minus n over 4d. Okay. And now by a similar argument, we know that the first term in the sum, each of these elements is at most 1. And they're also going to be positive by the definition of the good set G. So since they're positive and at most 1, I can square them, and I get the equation down below. And now what we observe is that the first term in this sum essentially ranges almost all of the data points. So the only points that it does not include are the bad set, whose size is very small. So I'm going to add and subtract the contributions of the bad points. So for the first term, the sum is now going to range over all the points in the data set, and then you have this inner product squared. And again, using the fact that the number of bad points is small, it's at most n over 4d, and each of these terms is again bounded by 1, the contributions can again be bounded by n over 4d. So the second term now picks up an extra multiplicative factor of 2. And now if we use the fact that R is a radial isotropic transformation, the first term is going to be at least n over d, and the difference of these two terms is at least n over 2d. And now what this says is that our approximate gradient is now positively correlated with any direction of low depth. So by iteratively taking steps along this approximate gradient, we will eventually converge to a good approximation of a center point. And now I'm going to conclude this talk with a few remarks. At a high level, you should think of this approach as being an alternative to previous approaches for center point computation, and it's based on techniques from continuous optimization, such as approximate gradient descent. And this new viewpoint offers a few new directions for future research. What are these open questions? The first is whether the polynomial in 1 over epsilon guarantees can be improved to a logarithmic dependency instead. And what one can show, given this improvement, is that this would now allow you to get an algorithm which computes a point with depth exactly omega 1 over d without incurring the approximation guarantees that we incurred in this algorithm. And the second question is that this worst case 1 over depth guarantee does not hold for every point set. So for example, with point sets that satisfy a large degree of symmetricity, you should expect to get much better depth guarantees. So for example, with like symmetric data sets, there are points with depth half, and the algorithm as it's currently defined is not adaptive to these kinds of nicer properties. So can we get algorithms that traverse the spectrum between like worst case point sets and really nice point sets which have these sorts of symmetry assumptions? And with these two open questions, I'd like to conclude the talk. Thank you for listening.